This zero detector is a collaboration from Lyon, France and Mexico. It's composed of about two detectors of scintillators detectors. This is B0A and B0C. And there are the select will be the select elements at level 0. Its aims are be part of the LB0 trigger for the experiment. It will be select from collisions of beam to beam gas, and it will be measure the impact parameter of the collision, the luminosity, and will validate the trigger of the muon spectrometer. His time of resolution have to be less than 1 nanosecond. Okay, the geometry of the B0 detector, okay, the ubication, it has to be, both detectors have to be in both sides of the point of interaction. Here's the point of interaction. So the B0C it's about 8 centimeters, and the B0 is a distance of 3 meters, more or less, of the point of interaction. So we can discriminate the collision between beam and beam gas because we know the time, the difference of time that have a particle to take from the point to the one detector and to the another. If we have collisions of beam gas, for example here, I don't know, we know the time that the particle take to go here to here. So it's more or less about 14 nanoseconds. So here is the geometry. The B0C and the B0A are divided in 32 cells. So we have 32 detectors in each one. So, for example, we have like divided like flashes of pizza. I don't know, like this, 8 sectors, and divided in 4 rings. So given plane. Given plane, we can define the reaction plane like the plane that forms in the direction of the beam, like the Z axis, and the direction of the parameter, the impact parameter that is in the axis X axis. So here we have two nucleus colliding, and this is like an almond if you have a collision, a non-central collision. And here it's the system. Here we'll have our plane, our reaction plane. So in this system of YX, we have this angle. If we rotate the system, this angle is our the angle of the plane of reaction. So we want to measure this angle, and we can get this plane. So first of all, we're interested of the flow. The flow is like the expansion of when you have the collision, you have like expansion of the evolution of the system. Inside you have the flow is produced by the old interaction inside of the constituents, the particles that are forming there. So they get like I don't know, the fireball expanded, and you have the flow. So you also in non-central collisions you have the anisotropic flow. So it's important the direction of this flow, and you can represent it with this a relation. And here is the angle of the plane, or the reaction plane, And we have also the coefficient of expansion. The B2, that is the second coefficient, is very important for us because we have like an elliptic flow in this form. Okay. So can you?
Go back.
Yeah. Please. No. Okay. Okay. I expect that in my detector, because it's a level 0 detector, I can see or the projection of this elliptic flow. So in B0 at CERN, with collaboration with Helsinki Institute of Physics, they are making this analysis. Here is the B0C and B0A relating in a collision of heat PV in 2.76 teraelectron volts in the center of mass, and we have a centrality of 30 and 14%. So there, in this case, we have the second harmonic or the second coefficient of expansion in the elliptic flow, and they are trying to relate these detectors to take this angle. Okay, so I'm trying to focus with the analysis per event. So I try to get a distribution of the phi angle. So if I have different sectors, each sector is have a phi angle. So I have a distribution, and if I have collision that is central, I hope that will be like a flat, because there will be all radial. The distribution will be radial. But in this case, I have no centrality. So I hope like it'll be like a synodal, like a period of my distribution of my particles. So I want to take a map of the B0C and the B0A of each detector. Here is a map of simulation, but with a lot of events. We have 15,000 events, I think, and I want for each event, only for see if I have the projection of the elliptic flow. So in this distribution, we don't separate still the primary and secondary particles. And the next step is adjust a distribution with a synodal function. And if this is possible, we can check if we can project this elliptic flow with a map of hits in the detector. So then we can separate the primary particles and compare the event plane that in the central barrier will be determined in the experiment. So B0 is going to determine the reaction plane per event. No, that's all.
Thank you very much. We've got time for a few questions now. Well, unfortunately, not time for, I think, Alex's talk. So with his agreement, I guess we'll take him up on Abhishek's offer to moving into Saturday. Questions for our speaker?
You were mentioning beam gas interaction. Where is that gas?
Oxygen. You make a vacuum in the LHC, but you don't have a perfect vacuum, so you can't have oxygen there. So it's so big, the accelerator is so big that you have the same chance to collide some particle with the oxygen than the beam.
With oxygen, what about nitrogen and other gases?
Sorry?
What about nitrogen and other gases? I mean, why oxygen?
What option? Because it's the, I don't know, you have air there, so
Yeah, but it's
you
predominantly-
think about oxygen. I don't know.
Are you concerned?
But you can, I don't know, it's, maybe it's another thing, but you're not interested in that. You're only interested in lead. It's the only thing that you want to collect. The other things, you don't take account about that.
I have a question. What sort of rate do you see in your detector? I mean, how many events per second?
In my detector, that's a good question. Okay. I don't know. Let me see. Our detector is so. I think that we lost a few events because we have a 1 nanosecond of resolution. But I don't know how many events we can lose.
Well, if there are no more questions, we'll thank our speaker again.